Okay, so let's continue then. So what we have talked about the first lecture is that this delay bandwidth product is the thing that makes things difficult to coordinate transmissions over a medium. And we saw that with this simple example of a two-station type of problem, sharing a medium where there is a certain propagation delay over this. But obviously, to coordinate two stations is not what we would like to do in practice. We would like to coordinate many, many more, for instance. So let's go into a few practical protocols to see how they are designed and what the pros and cons of these are. Okay, so actually one of the early protocols that was also practical for this is something called Aloha. And aloha is actually, if you know, it's the Hawaiian phrase for saying hello, I guess. So this was invented at the university or by a person that worked at the University of Hawaii. According to rumors, he was very interested in surfing, but his second interest was in data communications. So then he invented this protocol. And in a way, it's not much of an invention. So basically what we do is that we have a couple of stations. Okay, and the problem they had was they had many islands on in Hawaii, and they would like to communicate between these islands, and they had a satellite link over this, right? So there's a long delays and things like this. So basically the protocol is very, very simple. If a station has a frame to transmit, it transmits the frame and then waits for an acknowledgement. If the acknowledgement doesn't arrive, it waits a little bit longer and then retransmit the frame. Okay, that's it. Okay, so in a way, it's stop and wait with this extra waiting time, random backoff time. And the reason for the random backoff time we will see shortly. So it's stop and wait. You transmit a packet, wait for an acknowledgement. If the acknowledgement doesn't arrive in time, you retransmit. If we have station A, B, and C, so we have three stations now. So A, at this point in time, has data to transmit, and it simply starts to transmit that, the blue frame here, and then also starts a timeout counter. Station C also has a frame to be transmitted at this time, so it transmits it without any further ado, right? It just transmits this. At station B, these frames collide, and that we assume to be a bad event, right? So collisions here are assumed to destroy both frames, even though in radio this is not necessarily true. It could be that the blue frame is much higher power than the green frame, and then the blue frame would be decoded at B regardless. But for the purpose of the MAC protocols that we discussed now, we would just think of collisions as being inherently very bad, right? So we would like to avoid those. So anyway, so there is a collision here, which means that B would not send an acknowledgement for neither A nor to C. So after some timeout, if there is no backoff, then if it was simply stop and wait, then A would transmit this blue frame here, and the station C would transmit this green frame here, and these collisions would then keep on forever, right? So just stop and wait over a medium access controlled channel, over a shared medium won't work, right? Due to this constant collisions that would occur then. So what we need to do then is to introduce something called a backoff. Okay, so backoff here, what does that mean? It means that when station A does not receive an acknowledgement in time, when it times out, it waits a random time before transmitting again. So important is the extra waiting time, and also that this is a random time, random backoff. Okay, and the reason why it needs to be random is because C does exactly the same thing. So if C and A chooses the same backoff time, I mean, we haven't solved the problem, right? They need to choose different back-off times so that their future frames will not collide. Okay, so that's why the back-off time has to be randomized, and it has to be, I mean, you know, and it's different from time to time. So station A picks a back-off time here. The next time station A needs to back off, it selects a new back-off time. So it's not fixed forever. I mean, we select this on demand, so to say. Okay, now this back-off time here is chosen in some type of interval. So the back-off time is select from, you know, could be 0 also, up to some maximum time, TB max. This is the selection interval. So what we want to do then is to make the maximum time here large enough such that if we take 2 of these or a number of these back-off times, we resolve the collisions. Okay, so the longer the selection interval is, the higher the probability is that things will go well. The shorter it is, the higher probability there is that the back-off time is such that we still have a collision. You see this? Right? The longer that we can select, the higher the chances is that these 2 numbers would be such that we don't have a collision. So what is the problem of having a very large maximum back-off time? Anyone? Why don't we want this to be 10 minutes, 2 hours, 3 years? What is the problem with that? Nobody likes to be in a queue, right? Of course, if this is delay, right? The blue frame will not be delivered until this time. So if this is extensive, right? Minutes or seconds or hours, whatever, the user of that system will not be super happy, right? Because then there will be extensive delays due to this medium access control problem, right? So we want to make TB max as small as possible, but not too small, right? Because if it's too small, we get more collisions. So either we have collisions or we have delays. Both of them are bad, so we need to balance those, right? You follow me? Right. Okay. So how to do that? One way, there are many methods. One method is the following, is that and so basically the value of TB max depends on how many stations we have that compete for the channel at any given point in time. So in this case, there were 2 of these, A and B, right? But A and B does not know of each other's existence necessarily, right? So if there are many stations colliding on the channel, we don't know how many stations at any given point in time would like to transmit. Okay. So what we want to do then is then, or that's one way to handle this problem, is that we change the maximum the maximum back-off time adaptively. Okay, and this is called binary exponential back-off. And basically what it means that for each time we have a collision, each time we try to send the same frame over again, we increase the selection window. Okay, so here how it works. So at retransmission attempt K, we randomly choose an integer R in an interval from 0 to 2 to the power of K minus 1. Okay, so as K increases, the maximum value of R increases also. Then we select the timeout, the back-off time as this R, this multiplier R integer, times some basic time unit, time slot, T slot here, where T slot is chosen a little bit differently depending on the protocol. It could be, for instance, the propagation time, or the frame duration, or something like that. It depends on the protocol, which one makes sense, right? But there is some predefined slot time here. And then we take R and multiply that with T slot, and then we get our backoff time. And since R is randomly chosen in this interval, we get a random backoff time every time we do this. Okay, so the effect of this is that TB, the backoff time, tends to increase for each new retransmission event, right? As K increases, the maximum value of R increases, and therefore the maximum value of TB increases, which means that the realization of TB, the randomly chosen time, tends to increase as we keep on going through this, as K increases. So the average value of TB and also the maximum value of TB doubles each time we do a retransmission. So typically then, of course, for this to work in practice, there are also a maximum number of retransmissions before the protocol gives up, right? Sometimes you just give up. So a flowchart from this is that the following: the station has a frame to transmit, and then K is equal to 0. It's never been retransmitted. It's a new frame. And then goes there and sends the frame, okay? And then wait for an acknowledgement. If an acknowledgement has arrived, then we're fine. We're a success. Okay, so here everything went well. Now, if there is a collision or for some reason the ACK is not received, then we increment K. So the first time we go from K equals 0, it's now K equals 1. And then K is not greater than K max in this case. And then we choose R. And the first time we go through this, we choose R in the interval from 0 to 1. Okay, because K is equal to 1 here, 2 to the power of K minus 1 is 2 to the 0, so 0, 1. So R could be 0, 1 the first time we go through this, and then we wait either 1 time slot or 0 time slots. And then we transmit the frame. We go through the whole thing. Now suppose there was a new collision here. Then K is equal to 2 here. Okay, so this is for K equal 1. Now K equals 2, what's going to happen then? Well, we select between 0 and 2 to the power of K minus 1. So 2 up to 2 minus 1, 2 up to 1, 2. So it could be here 0, 1, 2, like this. Did I get that right? Okay, so to, yeah, 0 to 2. Okay, now K equal 3, we can between 0, 1 up to 4. K equals 4, it can be 0, sorry, it's not, and something a little bit fishy here. But anyways, in principle, this is correct. And then it's 8 like this. And then 16, 32, 64, right? You see, it increases very rapidly after a while. So we start by being optimistic and think that, okay, a small back off is probably okay. If we get another collision, oh, maybe there were more competition for the channel than we expected, let's increase the back off time or the maximum back off time. It's always random for each event, right? And then we keep on going this, and as you know, eventually we have a very large back off time, and then hopefully frames will go through. So any questions on this? The confusion I had, it was maybe this is 2 to the power of K minus 1. I don't know. But it doesn't matter, right? The big thing is that it increases exponentially. Okay, now going back to Aloha, so what is it any good? The first thing we need to do then is to, when we make an analysis here, we must say something about the traffic, the lambdas which are offered to the channel here, if you remember. So we'll make a small detour into Poisson random variables here. And Poisson traffic, or Poisson random variables, is used to model what? The number of independent events that occurs during a certain time period. Okay, so this could be, for instance, to model the number of requests for a certain document on the web server. How many of those are there per second, per minute, per hour? Or the number of frame transmission requests per second or minute or something like that. So something which is like happening, how many of these events happen during a certain time period. So for instance, if we have some events that happen, and then we select a time period, say this, and then we split the time axis into this, and then a number of events happen during this case. Maybe there's one event here, one event here, one here, one here. Here maybe no events, and it keeps on going like this. Like maybe here was like 2 events here, something like that. Okay, so it's something that this then the number of events here, which is 2 in this case, it happens to be 2 here, 0 here. Okay, let's make this 3 here. So the number of events that happens is something which is random. 2, 2, 0, 3, and so forth. And then lambda here is the average number of events that happen during this time period. So in this case, it would be like, maybe it's like approximately now 2 plus 2 plus 0 plus 3 plus whatever events that happens later on, all of this divided by the number of events. So in this case, we have only knowledge about these 4 events. We divide this by 4, and then what do we get? We get 4 plus 7/4. So on the average, 7/4 events happen each time period. So we can think of this in our setting. What we would like to model is the number of frames which are generated during a certain time period from all the stations which are attached to the medium. So it's the aggregated traffic that we would like to say model. So, and the statistics for this is typically then modeled as a Poisson random variable. So if y is a Poisson random variable, p for Poisson, lambda for its intensity, what it means is that the probability that y is the random variable, that there are k events during a time, whatever time interval we have proposed, follows this expression here. And the expected number of events is equal to lambda, just as I wrote here, right? So it's, lambda is called the intensity sometimes. High intensity, many events. You can think of this also as radioactive decay or something like that. It also follows this Poisson distribution. Or the number of light bulbs that cease to work within a certain time period. Typically also modeled as Poisson. Okay, so now if we think of having 2 random variables, z and y, and they are Poisson with different intensities, it turns out that the sum of the number of events, y plus z, is w, is also Poisson with the intensity, which is the sum of the intensities. Sort of makes sense, right? So if we had, for instance, one process with a certain intensity, another process with another intensity, if we add them together, we get a new process which has twice, the sum of the intensities. Okay. Now, so why is this? Why do we want this? Well, because we would like to say something about ALOA, the efficiency of it. And let me say this from the following: that all of this sort of derivation that I will present now is all bogus. It's not mathematically strict. it's intuitive, and it gives essentially the right result. Okay, so if we want to do this carefully, that would take 2 lectures maybe, right? And we don't want to do that. We just want to say something, yeah, you know, roughly how things work here. So this is, if one wants to do this carefully, it takes an effort, right? And we're not, in this course, not interested in spending that effort because the value is maybe not so high. So we will make a couple of very simplified assumptions here to get some intuition on what's going on, and then present the results. Okay, so assumptions. All frames have the same duration. So from all stations, we send the same number of bits per frame. During TF seconds, so we select TF to be our interval of interest. So the interval we have here will be TF seconds. During the TF seconds, the number on the average number, or the number of new frames generated for transmission by all the stations is Y, which is this Poisson random variable with some intensity lambda n. The number of old frames which are scheduled for retransmission, because some of these frames that we transmit through the medium will be collisions and has to be retransmitted. We assume that that is also a Poisson random variable with some intensity lambda r. And we assume that y and z are independent, so w, the total number of frames that we would like to transmit during TF seconds, is the sum of y and z, and it's a Poisson with the intensity g, where g is the sum of lambda n and lambda r. Okay, so maybe a block diagram would be interesting here. So we have entering into the system a number of new frames to be transmitted. These are generated in all the stations and are ready for being transmitted. They are transmitted immediately, right? So to the channel, all these Y new packets are sent. At the same time, there is a bunch of packets which have been sent previously but have been in backoff for some time, which is added to this. So the total number of frames we transmit during TF second is W, consisting of new packets plus backoff packets that are in backoff. And then these goes over the shared channel. Then, if we're lucky, some of these some of these frames will be successfully transmitted and they leave the system. Some of them will be colliding and they are then fed back into the backoff procedure, and then eventually needs to be retransmitted. So some packets go along in this loop until they pop out, right? And at the same time, new packets come in here. So this is the dynamics of the whole thing. Questions? So basically, new frames going over the channel, some of them collide, and then they are added to new frames at a later point in time. And some of the frames are successfully, right? And so we would like, of course, this to be as many as possible, right? And I guess in the beginning, if we have very few frames, just one frame, say, generated, then that will go through. If we then start to increase this a little bit, there will be more and more chance for collisions, and more things will be zooming around here, and fewer will come out, right? So as we turn up the intensity at the input, we've got more and more frames out until a certain point where we get less and less frames out. We are too aggressive, right? So let's formalize this. How do we do this? Now, suppose we have a frame and we're interested in figuring out whether this will survive or not. Okay, suppose we transmit this frame and we would like to track its fate. Okay, does it collide or is it successful? If it doesn't collide, we say it's successful. So we have a reference frame here, and it has a duration of TF seconds. So along a time axis here, there will be potentially 1, 0, or several interfering frames. So here we have a purple frame and a peach frame, and we see that these are somewhat overlapping with the reference frame. And if there is a little bit of overlap, we say we have a collision and then we lose the blue frame. If there is no overlap, then we say that the frame has been successfully transmitted. Okay, so that's the basic setup. We have a frame. Does it collide or not? That's the question. All right. We see now that any frame, interfering frame, which is generated from this point in time to this point in time will have an overlap with the reference frame. Right? So any packet which is generated, started to be transmitted during this point, this time interval, will collide with the reference frame. You see this? Right? So this purple frame, for instance, is started to be generated here, and then the tail end of the purple packet would overlap with the blue packet. There will be collision. The peach packet here is generated at this point, so the first part of the peach packet will overlap with our reference frame. So that's a bad collision event, right? And as soon as we get more than one, if we have one or several packets colliding with the reference frame is lost. So what is the probability for success in this case? Well, the probability for success is following. It's the same, it's the probability that there are no frames being generated during this time. Let me repeat that. We have a success when there are no frames being generated here, interfering frames. No interfering frames being generated during this time. So what is the probability for that? That's what we would like to compute. But before we do that, this time when we get collision is called the vulnerable time, or the vulnerable duration. And in this case, it's twice the frame duration. Okay, so we know that the number of frames generated during 2 TF seconds is a Poisson random variable, and it has mean 2WG. Okay, so why is that? Well, here W is the number of frames which are generated per TF seconds. Okay, so we get on the average G frames here, and on the average we get G frames here. During the whole period, on the average we get 2G frames. Did you follow that? Let's do it again. During TF seconds, the system generates on the average G frames. During the next TF seconds, the system generates on the average G frames. So on the average, during the vulnerable time, we generate 2G packets. Right. G packets here on the average, G packets on here, together 2G on the average. Right? Okay, so a particular frame, this reference frame, is successful if exactly 0 frames are generated during the vulnerable period, which is 2 TF seconds. So what is the probability that there are no frames being generated during this period? Well, it's e to the power of minus 2g. So this is the probability for 0 frames. And where does this come from? It comes from this. The probability that y is equal to 0 is lambda raised to the power of 0 0 divided by 0 factorial times e to the minus lambda, okay, which is e to the power of minus lambda. And in our case, lambda was 2g. The intensity, right, over 2 periods. Okay, so then we draw the following conclusion, that the number of successful frames on the average is the number of frames that we try to transmit, g, times the probability that these frames go over the channel. So it's G times the probability that there are 0 interfering frames, and at the end of the day we get G times e to the power of minus 2G successful frames. And it's successful frames per TF seconds, because the basic time interval that we have been talking about here all the time is TF. Okay? So I know this was maybe a little bit quick, but if you go back and look at this, and if you have any questions, you know, please come and ask me, because this is, the first time you see this is a little bit confusing. I know this. But on the other hand, I don't want to spend too much time on this, because at the end of the day, this is still just into, it's not a precise derivation, but it gives reliable results, sort of. Yeah, it gives at least a feeling for this, right? Okay. Now, let me ask you this: when you see this, can you find a way to make this better? What would you do if you had this protocol and you say, okay, I'm not happy with the performance here. Can I do something better in coordination of the transmissions? Maybe it's not super easy to see here, but the problem we have here is that any little collision here is deadly for the reference frame. So if we can do like this, that we say, okay, packets are not allowed to be transmitted at any point in time, but basically at some slot boundaries here, we would get rid of the partial overlap, because this purple packet here, it would destroy a packet which is transmitted here and here. So it can collide in principle with two packets. But if it's confined to be into a slot, it can only collide with one packet. So a packet transmission, if it's slotted, can only collide with maximum one other packet, right? So that's the idea of slotted ALOA. So what we do then is we divide the time axis into slots, and the slot size is the frame size plus a little bit of a guard interval. And the guard interval is to ensure that a frame which is transmitted in this slot will be received at all other nodes within the slot boundaries. Okay, so a frame that goes from A over the channel, it arrives at B at this time and at C at this time. And we see that the green frame here is confined to a slot. If we add a little bit of guard interval here, where the guard interval is greater or equal to T prop, right? Okay, so then the blue frame that goes from B goes to A here and to C here. We see that's still confined to the slot. The orange frame here is also confined. Here we have a collision event between the blue and the green, right? But we see that the blue collides with the green, and the green collides with the blue, but the orange one is not affected by this. And this is because we confine all transmissions to be within one slot. So a packet, the blue packet here, can only collide with frames which are sent in the same slot, not with the adjacent slots. Okay. Now, if we do the same analysis as we did before, we have here the reference frame and we have the interfering frames. So this is the reference frame. And these are the interfering frames. The vulnerable period for the blue packet here is now TF seconds. Right? Half of the vulnerable period we had in unslotted ALOA. And therefore, the probability for no collision is the probability that there are 0 interfering frames in TF seconds. Okay, and since we on the average we generate G frames here and G frames here, the probability that we generate 0 frames is e to the power of minus g, where it used to be e to the power of minus 2g for the unslotted case. Okay, so we reduce the number of collisions by a factor of 2. The probability of success then increases here, but not with a factor of 2. A factor 2 in the exponent, right? Okay, so curves, easier to interpret maybe. So again, G here is the average number of frames generated during TF seconds. Okay, and this means nu plus retransmission frames. Okay, so that's G. S is the successful frames. Again, frame per TF seconds. So S is the number of frames that leave the system successfully transmitted every TF seconds. So in the best of the worlds, we get 1 frame through every TF seconds. That would be the perfect thing, right? Then for every frame duration, we have 1 successful packet. We cannot have more than that, because then things will collide for sure. So for sure, S must be less or equal to 1, always. It will be equal to 1 if we have perfect coordination. But since we don't have perfect coordination, it will be less than 1. Okay, so what happens then is that as G increases, S increases also. And for slotted ALOA, it follows this. So this is for slotted ALOA, and this is for regular ALOA, pure ALOA. And it follows then, you know, these curves, right? So what is the throughput we get? Well, in the beginning, we see that, okay, suppose now we changed the intensity of the new frames, lambda n. So if we go from 0 and increase that, yeah, to something, we increase that. What's happening is that we start here, because the number of packets which are generated is low. It's basically just a new packet. And as we increase lambda, the number of new frames, we essentially get them through, right? So we follow a linear slope here with 1. All the new frames are also leaving the system. But eventually, we get into more and more collisions, and the number of frames which are leaving the system tapers off a little bit until it peaks at this point, and then it starts to drop again. Okay, and for pure ALOA, it peaks when G is equal to 1/2. Okay, now it doesn't mean that lambda n is 1/2. No, not at all, because G is the sum of new frames and old frames for retransmission. Actually, lambda n, we get that by going up here and reading off this value. If we're in equilibrium, the number of frames that enter into the system is also the number of frames that leaves the system. So this is lambda n for max throughput for Aloha. Okay, but at that point in time, we can see also that, okay, so what is it? Well, it's about 18%. Okay, so we generate, say, in a frame duration, the whole system can generate at most 0.2 frames. The whole system. The individual node, much less than this. But the whole system, maximum 0.2 frames per frame duration. So 80% of the capacity of the system is lost. If we're not happy with this, we can go to slotted Aloha. Oops, I don't want to do that. We can go to slotted Aloha, and then we see that the peak we can get for that is 37%. Okay, which is of course better than 18%, right? But still maybe far from where we would like to be. Questions? Yes.
What's the pro through Aloha over slotted Aloha?
Okay, very good questions. Why don't we always do slotted Aloha? It's because of this. The guard interval that you need to put in there, which is a function of propagation delay. So if you have very, very long propagation delays, then the guard interval could be substantial compared to the frame duration, and therefore there will be a loss which is not accounted for in the equations here. Yes?
How do you implement the time slots?
Yeah, so how do we, very good question. So here we also need synchronization, and that's another reason. So there is a little bit of overhead, or could be substantial overhead to figure out the slot, the synchronization to this. There are basically two ways to do this. Either that we have a specific synchronization protocol that transmits specific signals, so we synchronize the network. That's one way. That's actually done over the internet today. Another way to do this is that if we can afford a GPS receiver, we can derive universal time, global time, through the GPS signal. That's an expensive solution, but it's very precise, down to nanoseconds in that case. Very good question. Any more questions? Okay. So now, can we do better than Aloha? And of course we can, right? And one obvious thing to do is to, Aloha never listens to the medium before it starts to transmit the frame. So here, that seems to be a stupid idea, because if we can listen to the medium, and if the medium is busy, why do we send a frame? Because we know that that would basically just hurt the system, right? So the idea is to do a listen before talk protocol, and that's called carry sense multiple access. So essentially, when A transmits a frame, then it reaches B and C after a certain time. And if you always listen before you talk, so listen before the talk is that you sense the channel. If it's idle, you transmit. If it's busy, you wait until it's idle or you back off. There are different strategies here, but at least you don't transmit. If a collision is detected, we can back off and try again. And this is when you don't get an acknowledgement, essentially. And then the vulnerable period for such a protocol is equal to the propagation time. So what do we mean by a vulnerable period? Well, if A is transmitting a frame over the channel, then if C wants to transmit a frame, and if it listens to the channel here, it's idle, and then C would think that the channel is not busy during this period in time. So C can then start to transmit its frame, and then there will be a collision if it starts during this time. After this time, however, when it listens to the channel, it knows that it's busy. Okay, So we have a vulnerable period here also, and it's equal to the propagation time. And the propagation time is the maximum propagation time over the channel. Okay, so maybe we should stop here. So let me just then re-emphasize what carrier sense multiple access is. It's an improvement towards ALOA in the sense that we listen to the channel before transmitting the frame. If the channel is busy, then obviously we should not transmit the frame. This is not perfect, however, due to the vulnerability period. And again, the vulnerability period depends on the propagation time. So again, it's the propagation time that causes problems in coordination. The longer this is, the more difficult it is to coordinate. So when we meet next time, which is on Monday, we will talk about what to do when the channel is busy. Then there are different ideas on how to do that. And then we will talk a little bit more about practical protocols for this. And then after that, we will go over to scheduled or coordinated MAC schemes and talk about pros and cons with that. But that's a topic for on Monday. So see you then.